A mile and a half below the surface of Antarctica, buried in ancient ice, 5,000 sensors wait in darkness. On September 22, 2021, one of them recorded a faint streak of blue light, the signature of a single particle that had just passed through the entire Earth. That particle was a neutrino, and its energy, roughly 750 tera-electron volts, meant it almost certainly came from something violent, somewhere far away in the universe. The IceCube observatory sent an automatic alert within minutes. Telescopes around the world turned toward the patch of sky the neutrino seemed to come from, looking for the source. And they found nothing obvious. No active black hole, no gamma-ray burst, no X-ray flare, no optical transient. The usual suspects were all missing. But one team tried a different kind of telescope, one that sees not visible light, but sub-millimeter radiation, the glow of cold dust. Inside the neutrino's uncertainty region, they found something, a source so bright in sub-millimeter wavelengths that it was unlikely to be there by chance. They called it Shadow Blaster. Follow-up with ALMA, the most powerful sub-millimeter telescope on Earth, revealed something remarkable. The light from Shadow Blaster was split into 4 separate images, distorted golden arcs curved around a closer galaxy sitting between us and the source. That closer galaxy was bending the light from Shadow Blaster through gravitational lensing, magnifying and stretching a single distant galaxy into multiple copies. ALMA showed that Shadow Blaster sits about 11 billion light-years away, at a redshift of nearly 3. That places it in cosmic noon, the era when the universe was forming stars faster than at any other time in its history. And Shadow Blaster was forming stars at a furious rate, hundreds of times faster than the Milky Way does today, all packed into a core only about 1,500 light-years across. For comparison, our galaxy is about 100,000 light-years wide. Shadow Blaster was cramming an extraordinary amount of star formation into a tiny space. This is where the story changes. When a high-energy neutrino arrives from deep space, scientists usually look for a supermassive black hole, especially an active galactic nucleus firing jets of accelerated matter into space. Those jets are powerful cosmic particle accelerators. Shadow Blaster did not show strong evidence for a dominant active black hole. The likely engine here is the star formation itself. Here is how it could work. In a dense starburst core, like Shadow Blaster, massive stars burn through their fuel quickly and explode as supernovae. Those explosions send shock waves ripping through the surrounding gas, and those shock waves accelerate protons and other charged particles to extreme energies, creating cosmic rays. In a normal galaxy, many of those cosmic rays would escape into intergalactic space. Shadow Blaster's core is different. It is dense with gas and threaded with tangled magnetic fields, so the cosmic rays can get trapped. They bounce and spiral through the gas, colliding again and again with other protons. When a high-energy proton smashes into another proton in that dense gas, the collision produces short-lived particles called pions. Charged pions decay almost instantly, and one of the particles they produce is a neutrino. So the dense core acts like a natural particle collider. Cosmic rays go in, neutrinos come out. Light from the young stars is absorbed by thick dust. Neutrinos are not. They fly out of the galaxy, cross 11 billion light-years of space, pass through the Earth, and one of them leaves a streak of light in Antarctic ice. The idea that a dense starburst can act as a cosmic ray calorimeter, converting cosmic ray energy into neutrinos, is not new. Physicists have modeled it for years. What makes Shadow Blaster special is that a specific high-energy neutrino event now lines up with a specific compact starburst, rather than with the usual black hole-powered source. It is worth being precise about what this result says. The researchers found that shadow blaster is the most plausible electromagnetic counterpart inside the neutrino's uncertainty region. The probability that such an extreme submillimeter source would appear there by chance is low. But a single positional match, no matter how suggestive, is not proof. Confirming that compact, dusty starbursts really do produce high-energy neutrinos would require more associations like this one, more neutrinos pointing back toward more hidden star factories. Still, the modeling suggests this class of galaxy could account for a significant fraction of the high-energy neutrinos IceCube detects from all directions, possibly up to around 20% of that diffuse background. If that holds up, a meaningful share of the universe's most energetic particles may come from hidden factories of stars, buried in dust, doing their work at the peak of cosmic star formation. September 2021. A single particle crosses 11 billion light-years, passes through the planet, and leaves a flash of blue in the ice. 5 years later, astronomers trace the best candidate path back to a galaxy so buried in dust that optical telescopes could not reveal its engine. The likely source is not a monster black hole, but a small, furious region of collapsing gas, exploding stars, trapped cosmic rays, and proton collisions, all happening billions of years ago at the peak of cosmic noon.